Hola.
Hopefully you guys weren't waiting an hour. Hopefully you guys read the message.
What message?
That class is starting at 11
Um,
ish. 11:10 now. Okay, cool. Let's go ahead and get started since we're still gonna end at the time. I'm not gonna add time. So welcome back everyone. Happy Thursday or Thursday. Here's a goal for today. We're going to continue with lecture 6A. We're already in chapter 14.
Professor,
Yes.
can you please record?
Oh yeah.
Or
Yeah, I'm
are
recording.
you?
Yeah, I'm
Oh,
recording.
okay, I'm sorry. I saw it.
No, no.
Okay,
It's
I'm
always
sorry.
good to double, triple check.
I'm sorry.
No problem. So the idea is to continue with the in chapter 14, the first couple of sections of chapter 14, the principle of work and energy. And in the last lecture near the end, I did the derivation of that formula, and then it comes from Newton's second law and also the one of the kinematic equations that's independent of time. So I'll kind of, you guys want me to recap that a little bit?
Yes, please.
And yeah, and the next exam is, I think we agreed on Thursday. And it's going to cover 13 and a little bit of chapter 12. So what I'm going to do today also, I forgot to put a note on here. Let me put a note here that so I will send out we'll post a practice exam. Cover these topics. I hope that's fair. Okay, so 14 is being covered, but it's not going to be on the exam, but we're going to continue with the concepts. Okay. Any other questions? The other thing on my agenda is I'm going to post a couple of quizzes so you guys can work on them. They're not going to be all due on the same day. I'm going to stagger them so you guys can kind of work on problems from that will be similar to what you expect on the exam. Okay, so you have it won't be, you have time like to complete them. So just be on the lookout for that. Let's see, and then yeah, I'll post a practice exam with the solutions. All right, let's go ahead and move forward with the lecture. And let's see if you look at what happened here. Look a little messy here. A little derivation. Okay, so it's, and I'll recap it like this. You guys can go back to see how we did the derivation, but if you notice, you recognize this formula, ADS is equal to VdV, right? And you recognize this. Sum of the forces is mass times acceleration. But if I look at it in the normal tangential, some of the, you're going to have two forces, right? You're going to have forces that are normal and forces that are tangential. What's important, right? Let me see if I can, what I'll do is I will write it here, right? And here's the idea. And it goes back to the same, here's the particle. A little more here. Here's the path of the particle. Okay, 2D. The particle starts at state 1, and then it ends at state 2. So the particle needs to move along the path to get to state 2. How do you move it? How are we going to move this particle to get it from state 1 to state 2?
You apply a force.
Yeah, and when you apply a force, you got to make sure that what we really care about, and remind me, what is Newton's second law? What is Newton's second law?
F equals ma.
Yeah, F equals ma. But here, I'm going to be very specific. The sum of the forces vector, because it matters the direction, The sum of the forces is equal to the mass times acceleration. Vector,
That's right.
right? So I have to be very specific with the sum, the net sum of the forces. We also, let's kind of now project it onto a known coordinate system that we kind of played around with or learned about. One coordinate system that we can look at is, let's look at it where this axis and this axis. Do you recognize this axis here?
NNT.
Yeah, that's the NT axis, normal tangential. Cool. So then what happens is that the formula F equals MA, you're gonna have two of them. You're gonna have, if I look at along the U tangential unit vector, right? If I actually draw the unit vector, it's gonna look like this. There's a UT unit vector, and then there's a U normal. Notice that technically it's supposed to be attached to the particle, but it gets messy, right? And so you guys remember that as the particle moves along the path, that unit vector starts to rotate, right? But then that's where you start getting this centripetal acceleration and all this other stuff. Okay, so if you look at the scalar formula of that, what you're going to get is a scalar. You're going to get the sum of the forces that are normal is equal to the mass times the acceleration. That is actually not that one. The sum of the forces along the tangential is equal to the mass times acceleration tangential, right? F equals ma. If you look at the normal, the sum of the forces in the normal, all the sum, if you go back to the problems that we were doing with the FBD KD, right? The whole point of all that is to break down the forces into each component, right? Even in cylindrical, we have to, okay, what's the radial component? What's the theta component? And then what's the Z component if you want to look at it in 3D? But we've been doing that. That's consistent. We've been doing that in chapter 13. If you look at the normal, it's mass times acceleration in the normal. But we learn in the kinematics of a normal acceleration that normal acceleration is equal to the velocity along the path tangential to the path over v squared over rho, right? Then, and when you look at this, what do we know about this AT? How do we get this information? This AT, it's the same AT from these kinematic relationships. Remember these? Velocity is equal to ds dt. Acceleration is dv dt. These are always important, right? ADS is equal to v dv. These are your kinematic formulas from chapter 12. But I want to be very specific that if you look at, I'm going to zoom in here. If you look at your S, that's along the path, right? That's how much you displace, infinitesimal displacement along the path. And then that means your velocity is along the path, right? So it's tangent. Your velocity is always along the direction you're going, right? And then if you look at number 2, the acceleration, you have 2 types, right? The acceleration that we're talking about in this formula is not the normal acceleration. It's the acceleration along the path. If you're in your car and you're going along this curved path, the acceleration is you hitting the accelerator. It's the acceleration along the path. That's why I call this one AT, right? That's not AN. AN is different. It's dependent on your tangential velocity. I hope that's clear, okay? And so that means you're taking, right, AT is the derivative of your velocity tangential, okay? And so what was number 3? You plug in number 1 and 2 in terms of time, put it together, right? This is the one independent of time. So then the acceleration tangential is equal to VT dV, okay? So then what is this principle of work and energy, okay? The way I proved it was I got this formula, and you guys can go back. I got this formula, and I got this formula. Because what I said was for number 3, let's just do a little bit of fancy math. A tangential is equal to what? If I just solve for A tangential, it's VT dV over ds, right? I just kind of moved it over. And so all you have to do is, if you want to have forces tangential, it's going to induce a acceleration tangential. So all you got to do is plug in this one. Okay, so then if I plug it into here, if I plug it in, And let's look at the sum of the forces. Okay, mass times acceleration. If I plug it in, what am I going to get? Vt dv. Actually, I should have put another t in there. Dv dtv dv vt dvt. That's why I don't like putting too much notation, but I'm putting it here because I want to be very specific as to what we're talking about. So this one, just the velocity tangential. It gets kind of messy, but again, I'm being specific. Okay, so then you have dv dt, okay, over ds. So all I'm doing is I plugged in here is a t, okay? And so the step you're going to do here, and I'll explain conceptually what's happening, okay? That's AT. This whole thing that I put in parentheses is AT, all right? And so what I'm going to do is let me package it again. Vt dvt over ds. The mass is conserved. The mass is constant. So that means if your particle is moving from 1 to 2, you're not losing mass. It's not a rocket where you're burning up fuel and the mass of the rocket is less. Okay, so it's a fixed conserved mass. Okay, so what I'm going to do is just multiply by ds on both sides. Okay. And so what you're going to get is m v t dvt. Okay. So here's what's happening here. It's a sum of the force, but what's the subscript here? What was that? What was the subscript for the sum of the forces? Anyone?
Tangent?
Yes, tangential. So here's what it's saying, okay? You want to do a little bit of work, right? So actually let me finish this derivation, okay? Let's see. Yeah, here's what this formula so far is doing. But you guys see, this is just algebra, right? I'm nothing fancy here. No, right? I'm just plugging in, solving for it based on stuff that you know. But here's what it's telling you, that if you want to know what work you're doing, but the work you're doing to move the particle, you're moving it how much? Look at this little concept here, ds. You're essentially moving the particle how much along the path? You're displacing it a little chunk ds, right? Infinitesimal amount. And so your force acting on that, you have to add up all the forces, right? Here's your force vector. That's the force vector. But if you really want to move it along the path, you can't just use the total vector, the total force vector. You want the force that is what to the path? Tangent to the path, right? So in order for you to do work, your force has to be along the path. That's why if you look at this notation, this force has to be tangent to the path. Okay. Now, what if your vector is not tangent to the path? If you know this angle, you call that theta, don't you have to hit it with cosine theta to get it? Right? So if you recall from your physics class, if you want to know the work to go from, let's say, point 1 to state 2, if I want to move the particle from 1 to 2, from here, let's see if I can move it. If I want to move it from 1 to 2, meaning it's moving from 1, and you're going to move it all along the path to 2, right? What work was done? So if you want to know the total work from 1 to 2, what you need to do is add it all up. And a fancy way of adding it up is you add up all the work from 1 to 2. And if you look at the sum of the forces, you're going to look at the whole vector, right? But then you're going to do a dot product along the path. because S is actually, remember S is a scalar, but you actually look at the position vector. Remember how the scalar and the position vector, S is the same thing. R and the S are the same thing if it's infinitesimal. Go back to like chapters 12 stuff, okay? But this is your work formula. They had a dot product from your physics. And the reason why you wanted this dot product is what? You only wanted the force that is what to the path? Tangent to the path. So what would you do mathematically? You remember from statics that it's just, if I look at the scalar, it's just F cosine theta times your whatever your delta R displacement is, right? It's force times like the distance along the path. And so if you look at this force times cosine theta, this is like my force tangent, right? And the analogy is this. A quick analogy is this. If you're trying to, I think I used it last time. Let's say if you're trying to move a box, right? And you're pushing the box. When you apply a force on the box, you apply a force vector like this, right? Let me be a little bit more, let me give it a different angle. Push it. Long arms. Okay, so if you push this, you're going to apply a force like this, a force vector. And the box could only displace, let's say on average, it could only displace that amount. But notice that only the direction you can push it in is what? Along the x-axis, right? So if you look at your force vector, you have to realize that the force vector, in order for you to move the box along the ground, in order for you to do work, to move the box, your box could only travel in the x, right? So then the only way this box could move in the x, which force component do you want? You only want the force that is tangent or along the x-axis, along the path, right? And so in order for you to get this one, if this is theta, then you have to hit the magnitude times cosine theta. But that's a take-home message, that the work is force times distance. But that force has to be along the path. That's why you use dot product, right? In your little integral, the fancy calculus way of saying that. Does that make sense? So is that clear? Thumbs up if that fundamentally makes sense. And that's essentially what's happening here. Okay, so, and if not, let me know what in particular. Okay, so what happens is, and here's where it gets a little bit more complicated in that if you look at the particle, let's say at some intermediate point, 1' or something, right? The force could be, the force vector could be different at this point, right? And so you have to, and then the tangent is also different. The tangent is not the same tangent as before. So at all points, you have to get a function, right? You have to do the integral of that. A lot of the problems it's going to be rectilinear. So it's not going to be as bad as you may think, but it can get crazy, right? Because what if you go on a curved path? What if the force changes with position, right? But most likely where forces are going to be constant, okay, along the path. So now, again, let's go back to this. If you want to know what is the total work to move it from 1 to 2, again, you look at the net sum. You can have all kinds of forces acting on the box, right? Let's go back to this box example, right? Yes, you have a force here, but here you're going to learn later on that, hey, look, what happens if I introduce friction? What if I have a friction force, right? Or what if someone else is pushing F2 this way, right? Wherever the net sum of the forces, it doesn't matter. All the forces that contribute to the box either moving to the right or moving to the left, you have to look at the net sum. So you have to look at the net sum of all the components that are along the path, tangent to the path. So if you look at this notation, what this is saying is, look at all the forces, the sum of the forces that are tangent to the path. If it ends up being that all the forces tangent to the path are 0, then that box is not going to move. But if there's a net sum of forces tangent along the path to the right, the box is going to move to the right. You're going to do work. So if you look at it here, the infinitesimal little bit of work is just that force tangent times that little displacement ds. That's work, force times distance. What kind of force? The force tangent to the path, along the path. Okay. But what if I want the total work? Don't forget the picture. What if I want to move it from 1 all the way to state 2? What is the total work? Just add it up. So when you add it up, and let me bring it here. Some of the forces tangential ds is equal to mvt dvt. Okay, so if you add it up, all you're doing is you're integrating from 1 to 2. Add it all up. And because the mass is constant, I'm going to pop out the mass, which is constant, out of the integral and integrate from 1 to 2. Okay, and so this whole term, what I just did here, is the total work that I did to move it from state 1 to state 2. It's force times the distance, independent of time, right? This is all independent of time because we use the third formula, which is independent of time, force times distance. And so what is the stuff on the right side, right? What is the stuff on the right side? The left side is already a term. We'll start using that. On the right side is going to be the energy, because I don't know if you recognize this term right here. What is this? What is MV? Do you guys recognize it? Have you guys seen this?
Mass times
MV.
velocity.
Yeah, there's a
Momentum.
special that's called momentum. And because this is moving in a straight line, in a linear line, right? So is rectilinear. And it's not necessarily a straight line, but it's moving along the line. It's called linear momentum, right? Because that particle can't rotate. It's not a body, right? So it's called linear momentum. So, but you'll see later on in terms of energy, we can look at that. It's called the linear impulse and momentum formula, which is derived differently with time. Similar fashion. But here's what if I integrate it. So that should kind of tell you it's you're adding up all the momentum change, right? If I go faster, don't you change your momentum? If you go at a faster rate, you increase your momentum. So all you got to do is so how did you increase your momentum? By adding this force pushed you to go faster along the path. So you're changing your momentum, which should affect you're increasing your energy, because energy is a measure of how the kinetic energy is a measure of how fast you're moving, right? And you get that from here. So if you integrate, what is the integral of v dv? Ignoring the t concept. That is mv t squared over 2 integrated between state 1 and state 2. Right? What is the integral of x dx? X squared over 2. And so now when you evaluate this one here, you're going to get the velocity and tangential squared over 2 for, I think it depends on the rotation, but right now I'm just going to say for state 1, right? Minus the mass times velocity over state 2, over 2 of, sorry. First one has to be evaluated as state 2, and this is state 1, okay? But you should see that this is very similar as 1/2 mv squared. By definition, depending on your book, this is called T or KE. This is called kinetic energy. This one here is the kinetic energy at state 2. This is the kinetic energy at your starting point, right? Didn't the particle start at state 1? And so if there is some change in energy, right? If there is some change in kinetic energy, that if it went faster, most likely it's because a force pushed it to go faster, right? If you have a rocket, what's the rocket going to do? You turn on your rocket, you go faster.
Sanandaji
Right?
email.
Yeah, Sean, I think you unmuted. So the rocket thrusters applied a force over some distance, which increase your energy to go faster or go slower, right? You could have reverse thrusters. So here's the general formula that if you want to know what is energy, I'm going to rewrite it like this. So right now it looks like this. The work from 1 to 2 is equal to the kinetic energy for state 2 minus the kinetic energy for state 1. But what I want to do is what is the kinetic energy at state 2? If you want to know if I started at state 1 and I did work to move it from 1 to 2, what I'm going to do is I have my initial kinetic energy, state 1, and then I'm going to add the work to move it from state 1 to state 2. All I did is got this term here and moved it to the left. Okay. Moved it to the left just algebraically, and then I'm left over with kinetic energy 2. So this is what it's saying. Okay. What if a particle at state 1, what if it's already moving at some energy? What if the velocity is equal to 25 miles per hour already, right? So if it's already moving, it has momentum and already has energy in the initial. But then what if I turn on a rocket whatever, this rocket to kind of move it along the path. So what is the energy at state 2? Well, in order for you to move it from state 1 to state 2, what must have happened? You had to do work to move it. What did you do? You looked at the sum of the forces that are tangent along the path, and you summed it all up from 1 to 2. You look at the forces along the path to move it faster along the path. That's what work from 1 to 2 is. And then if I add up the kinetic energy on the left side, kinetic energy is 1/2 mv tangential squared for state 1. And it's equal to, on the right side, the final, well, what is the speed, right? What is the speed here at V2? Right? What's the velocity? The velocity, you get that by solving for it on the right side of the formula, which is 1/2 mvt for state 2. Does that make sense? So this is energy. This is also energy. But this is specific. It's the energy of motion, which is kinetic. Energy of motion. And then this one here is work of a force. Force times distance. That's why this whole thing is called the principle of work and energy. Any questions? Because this is just the main formula and we're ready to start. I think we're ready to start solving problems, knowing how to use this. And any questions? I kind of did the derivation again. And I know I brushed it last time, but good. Are you still with me? Did I lose you, or you're still with me, or anything? Anything? Let me know you're still awake. Okay. Again, and I want to make sure I reinforce this, right? You don't look at any force. You look at the force that is tangent to the path, and you could only move along the path S. And the forces have to be along the path. Okay. Friction always opposes your motion. So if I bring in friction, you have to look at the net sum, right? Look at the net sum. So that's a key thing. Not just any force. Normal force is not going to do anything. It's just going to keep you on the track, right? You have centripetal acceleration. Cool. And what's important is, look, it came from formulas that you kind of played around with in chapter 12 right here and chapter 13. What is 14 doing? Piecing them together. Okay. Chapter 12 and 13 for a particle. Cool. So our goal here is calculate the work of a force, apply the principle of work and energy to a particle or system of particles. Would have multiple. What if I have multiple? But most likely the problems you get are going to be a single particle.
Could you go back to the last for a quick second, please, Professor?
Sure.
Thank you. Lower down. Where exactly we were? Yeah, exactly, please. Thank you.
Okay, so let me poll to see if you guys, hopefully you're done processing, Alejandro. Let's see here. You process, I like to say I let it marinate. Okay, first question. What is the work done by the force there to move it from state 1 to state 2? The particle, you're moving it from 1 to 2. There's the force acting at all times. What is the work done? A, B, C, or D? I'll give you guys 30 seconds. Should be quick.
Professor, is this why we have MATLAB? So we could put in all those little pieces here and there and then not skip any because of human error, or?
Well, you can develop programs to calculate the work along the path if you know it, like analytically. But the person, the programmer or the MATLAB engineer is gonna, if they're already, they're the ones programming it, right? So you still have to kind of look at the theoretical solution, and go back to make sure you're not doing any errors, because your code could have human error to begin with, right? But you can
No, what
actually
I mean is
calculate it. Yeah.
you could put in like, you have static friction, kinetic friction. This is where you increase the, speed. I mean, increase the force so you can push it harder. This is where you push it
Yeah. Oh yeah.
softer.
You can start having variables and start optimizing things. Like what, so you start having questions of, okay, what force do I need to get to this speed, or what happens if I have this drag wind force, and what would it do to the projectile motion? So you start modeling. But then again, at that stage, you probably have some companies that have modeling software that's already kind of designed, or you can use MATLAB to create your own with the understanding of this fundamental Newton mechanics, right?
This is
Okay, how
very
are we doing?
scary.
Oh no, it's not scary.
Cute.
Scarily awesome. Let me say 9.
Very
All right,
cute.
I'm gonna
That's
end the
awesome.
poll. I'm gonna end the poll here. Oh, 4 of you are still sleeping. I'm gonna unmute you guys. You know I have the power to. I'm gonna hear some snoring. Okay. Oops. Okay, so 50% of you say C, 4 and 3 of you between A and B. Okay, so the work done is, well, look at this. And here's the important point, that the particle could only move, the particle can only move in this direction. The force is perpendicular. How, if I mean, now, doesn't it make sense that if a force is upward, shouldn't the particle move upward? Right? But it's not. It's moving. It's actually moving this way. So if that's the only force acting, well, guess what? This force is not going to push it. This force didn't push it that way. A mathematical way of saying that is, we'll get your force vector and dot it with your displacement vector, right? F cosine S theta times S. If you want to look at the magnitude. Why cosine? Well, because work is force times distance along the path. And right now your angle is 90 degrees. And what is cosine of 90? 0. So you're not doing any work. So the answer is going to be 0. Because the force is perpendicular to the path. Didn't we say the force has to be tangent to the path or along the path motion? So there's no work. Does that make sense, everyone? I hope that's clear. So let's look at the fundamental, the calculus definition of what we're talking about, work. The scalar formula. And you guys can look at this little picture, right? I kind of already alluded to this, right? I showed you guys, but the book obviously has better pictures. Let me do another poll. So here's the question. If I'm moving the particle, let me highlight the points. The blue line is the path. Okay. You move the particle from state 1 and state 2. You moved it along this line, right? And right now it's showing it to you at where it's at instantaneously. It's still moving. It's just I took a picture and it's along the way, right? So the question is, well, what is the total work done? And it's a scalar formula between state 1 to state 2. I didn't do S1, S2. I just kind of like I do 1 to 2. It's implied that it's S, right? Because it's your variable. You see how the normal tangential coordinate system is there, how it's established, and then the force vector. This force vector is a sum of the forces. You look at all the forces acting on it, but the ones that are only going to move it along the path, because that's what work is when you move it along the path, is which one? Okay. I'm going to give you 10 more seconds. Okay, I'm going to stop. Okay, so we get the majority of you saying A, 4 of you B, and a couple of you for C and D. Okay, so we agree that forces that are normal, right, should not push it along the tangent direction because it's normal, it's perpendicular, it doesn't do any work. For the same reason above here. This is like a normal force, if you want to think about it. This is like our tangent, and this is normal, if you want to look at it in terms of this direction. So for sure, you cannot have the normal force. So D and C can be eliminated right away. Now the difference is, well, look at what is the difference between A and B? Well, the only difference is one is negative, one is positive. So it has to be the positive version. Okay, it has to be, by definition, you're going to assume that it's the sum of the forces is going to push it along the direction. What it can be, how do you get a negative? It can be that when you do the sum of the forces, it could be that friction wins out. And so this term alone can come out negative. So by default, it has to be positive, but you can have a net sum of the forces that are negative. What does that mean? That means it's going to have an opposing force. So the particle is going to move in the negative direction. That is negative work, right? When you're pushing something forward, that you're doing positive work because you're going along the same direction. If you're pushing something back, that is in the opposite direction of where it's moving, that is called negative work. Does that make sense? Negative work. And where do you get that from? Let's do F dot R. The magnitude F dot R is F cosine theta times R. Okay. So here's the dot product, right? Here's the reasoning. Let's say the box. Okay. Let's say the box, the force, the box can move in this direction. And that's let's say it moved a distance R. Okay. That's the box. And so that's the positive direction. Let's say it's the positive. But then if the box, right, if there's a force in this direction, right, opposing the positive direction of motion, is that positive or negative work? That
Negative.
is going to be, yeah. So yeah, because if you look at them, just think of it as vectors from statics, just general vectors. If you have a vector R going in that direction, and then you have a force vector this way, right? What is the angle between them?
180.
180 degrees. So then all you got to do is say, okay, forget what, I don't know what F is, the magnitude of F, cosine of 180, and then times R, whatever that magnitude is. Well, what is cosine of 180?
Negative.
Negative 1, right? So then you're going to get negative work. Okay. So it depends on the net sum of the forces. So that's why we look at all the net sum of the forces. Okay, so we'll kind of go ahead and move forward. I'm going to quickly do go through the slides here. Are we? Let's see here. You guys can look at that, but there's pictures of what we're trying to say. Work, for the book uses you. I totally forgot
It's the same thing as work, right?
Yeah, it's the same thing as work. I want to be consistent. To me, W, U, it's kind of like the same thing. And notice how there's a cosine in there because you're using dot product, and that's the formal definition, right? I kind of to show that the work to get it from 1 to 2. So U, and again, depending on the book, for some reason I remember W. To me, it makes sense. It's W because it's work. So we can go between them. Okay. So the book uses U, so
But
I'll be synonymous. Go ahead.
what is the symbol for angular momentum?
Angular momentum is actually a cross product.
No, what is the symbol?
Oh, the symbol is going to be H for this book. H vector.
No, but normal world.
What do you mean?
Like, cause doesn't that like omega look like a W also, or?
No, angular momentum in this book is H, which we'll get there next chapter.
Cause what is the one that like or looks like a W or the Greek letter?
Oh,
That-
omega.
Omega.
Oh, that's omega is angular velocity.
I'm sorry. No, go. I don't know. But
Here.
yeah, I'm sorry, everyone. But yeah, because that's why, because that one would look like the W, and that's why.
Oh, I see. No, but I do. This is supposed to be a capital W. It's lowercase w. I see how. That's why I do these little wings here. Capital W. That's a good point. Okay, so I'm going to move forward because of this. The slides are that you guys can do that. Look at the components, right? You're projecting in the components onto the x-axis. You use the cosine. You guys
Thank
can go
you.
back to that. So now here's what I want you guys to focus on. There's going to be a couple of things that exist in your problems. We know if you have some of the forces that are acting on the body along the direction, it's going to do work. But what happens if you have a particle moving in a gravitational field, meaning you have the effect of gravity? And I want you guys to think about it this way, okay? And before I go to that slide, okay? So think about it this way, the simplified form, then we'll go back to this picture. Okay, so now look at this ball. Okay, gravity is acting down G, okay? So this is your standard like gravitational field, right? X and Y. Okay, so let me ask you this. What is let's say it's a ball, it has the only force acting on it, acting on the ball, let's say it's there. What's the force acting on it only?
Gravity.
Yeah, the gravitational right force. So that we're going to call the weight force. Acting down. Okay, let's assume that's the only force for now. Just the gravity force. Okay, so now look, what if the particle moves in the vertical direction? So let me go back down. What if the particle moves vertically in the positive y direction? Okay, so let me ask you this. Do you think, is this positive work or negative work if I'm doing this?
Negative.
Why is that negative?
You're going against gravity.
Yeah, right. So you're going against gravity. So if you think about it, the particle is moving up, but guess what? The force is moving down. Aren't they opposing? So, or if you want to think about it, you're going against gravity. So because you're going against gravity, that's negative work. The force vector and the direction vector in which you're going are opposing. So if you want to think about it mathematically, that's negative. That's cosine of 180, right? So now what happens if you do this? What if I start from the top? What if I start from the top and I go down in the y? So what if here's the ball or the particle. I'm going to move it down. So moving down is down. And now if I move it down, isn't that the weight direction? Right? So you're going with gravity. Is that positive work or negative work? So if I go down, that is positive work because the weight vector, the force, is along the same direction you're displacing, you're moving. Does that make sense? Okay, so just think about that fundamentally. So here, let me throw you the math. Okay, so if the assumption is, and look at how the weight force, the only weight, it's a body force, the only vector, right? Let's say a particle only under the influence of gravity moves from state one to state two. Okay, so if you're moving from state one to state two, here, I'm going to show you the animation. So at all points, gravity is acting, right? So but here's the thing, gravity only acts in the y. So the only thing that's going the work, if you move it from one to two, going to a higher position vector, the work is only dependent on your change in y. Does that make sense? Because when you do a dot product of two vectors, the whole idea of dot product is you want to make sure the vectors go along the right direction. They're in the right direction, right? And collinear. That's the whole point of the dot product. So if I want to treat the weight vector by itself, I'm so comfortable with weight vector being down. What I'm going to do is, well, don't I need the displacement that goes along, right? Don't I need the displacement that goes along the direction of the vector, right? If I want to know my displacement, don't I care about the displacement that lines up with the weight vector? If I want to preserve the weight vector, that distance is delta y. Do you guys see that visually? So you only care about how you move in the y because that's the weight vector. Notice though that we're so used to this form that F has, why don't we project the force vector? Well, you can do that too. You can keep your position vector, but then now you have to project the weight vector. At all times you have to project the weight vector that is tangent to the time. So it's a little, I don't want to get too much details in. I'll prove that to you later on. But dot product is you have to just do the vectors have to line up, okay? But the formal definition to make things easy is let's not mess around with the weight vector. Leave it alone. Don't do your f cosine theta. Leave your weight vector alone. So then if I dot it with a position vector, because don't forget, if weight dotted with your position vector, what you're saying is let's look at the component that is projected onto the weight vector, meaning that component projected onto the weight vector is your delta y. And that makes sense, right? Because if I want to do work against gravity, I'm only going to move in the y or move it down in the y. Does that make sense? So if you integrate along some crazy path, well, what's going to happen is really the weight is constant, always acting down, right? So if the weight is constant, you integrate it, you pop it out, and then you get your change in displacement from y2 to y1. And the assumption is you're going against gravity, right? So you go up to a higher point, and so the work is going to be negative delta y. Okay, so if I want to calculate what does the work do to the body force, the weight force, it's going to be negative w delta y. And it'll become, don't worry, it'll become positive if I go from a higher point to a lower point because your final state is lower. Okay, so just keep that in mind. Any questions as to this one? Just have this as one of your useful formulas. And again, it's using u. I'll probably start switching to that notation. Just to be consistent. Questions on that? Does that make sense? I'll hope to clarify it when we start doing problems, okay? And again, it's our systems are going to have gravity in there, and there's going to be other components, and we're going to have to figure out what how it's going to work. Okay, good. Thumbs up. Unless I'll move forward. Okay, so now what is the work of a spring? What if we have a spring attached to the particle? Okay, what is it doing to the particle? So how do we first find the energy, right? Don't forget that if I have a spring, the spring could displace, let me see, put it here, here's before, right? Here's before. And let me first talk about it simply, then I'll go into the little fancy little math. If I have a spring and I displace the spring, make it longer, right? You're gonna get some from the original to here. You're gonna get some change in length, right? And why did it change in length? Well, because you applied a force. Okay, but notice the force is what? the force is along the direction in which you displace the spring, right? So if I want to find what is that force, well, the total force is just equal to the force of the spring Fs. It's already along the path. So then all you got to do is integrate the force of the spring along the path. So I can just multiply. I don't have to do dot product because it's already along the same direction, right? The force and the way it stretches, it's already there. And then what you guys do, what you learned is that when you model a linear spring, it's equal to the spring constant times its displacement, right? S, or you can call it in general, S is like our delta S, because what matters is your relative displacement. Okay, and so does that make sense? Remember, the force of a spring is K times S, and so if you integrate this, you're going to get the work of a spring. Well, let me plug it in. A S ds from 1 to 2. So what do you get here if you integrate it? K is a constant. So if I pop out the constant, you're going to get K S squared over 2 from 1 to 2. Okay, clear here? The variable, all I'm doing is adding the work done on the spring. To stretch it, to compress it. The spring only, okay? So if I evaluate this, you may see this. Remember that you've probably seen this in your physics. Oh, what's the energy of a spring? To go from state one to state 2. The energy of the spring is 1/2 K S2 squared, 2 being state 2 minus K over 2 S1, state 1. So if you want to know what is the work of a spring, from 1 to 2, that's it. And S is the relative displacement, okay, to the undeformed. So let me go back to the formula here. So what I just showed you, what does the book use as a notation? Yeah, it's the same U. It's a general U, right? But when you have a spring, notice that, see, this formula is the same thing. The energy of a spring is going to be that formula. Okay, we'll see it in practice. Yeah, this is probably the tricky one. The S2 and S1 definition is going to be tricky, but I'll guide you with it. Okay, questions on that for the spring?
So force of a spring and energy of a spring are interchangeable now, right?
No, they're different. They have the same units. They have the same, right? But one is work and the other is energy. We'll learn about energy methods later. This is not the potential energy of the spring. It looks similar, the math, but we're looking at it differently. It's how much force is needed to displace it. Okay. It's going to be very similar. So when we get to energy, I'll try to like pair those two. But I want you to think about it this way. I'm applying a force. How is it going to displace? That's what FDF is. Okay. It's the work to move it from 1 to 2. Okay. It's the work to move it from 1 to 2. So what is energy in terms of the potential energy of the spring? It's the ability of a spring to do work. It's not the motion of moving the spring to another. Just like, potential energy, MGH, it's the energy of the potential to convert something based off from some like a cliff or something or whatever it may be. So it's a different type of thing, even though the map is similar. Okay. So we'll go into those details when we get to energy.
I'm sorry, I just don't get it. Say it one more time. I'm sorry. You're saying it's similar but different. It's like, okay.
Yeah.
But I'm so sorry, Professor.
Okay, no, so check this out. Here's the spring. No, I'll try to explain it this way. And it's not stretched. Okay, so now the spring is stretched. Okay. You stretch it a certain amount. Okay. Now, and you're holding it there. You got a spring, you stretch it, you're holding it. Is there energy stored in the spring?
I would say yes.
If you're holding
but that would be wrong.
Okay. Yeah, if you're holding it, you feel the spring wanting to,
Yeah.
it has the potential to go back to its normal
Unless you
equilibrium.
heat it and then you
Mhm.
deform the spring constant and you like
Mhm.
suck that out of it.
Yeah, so it
Yeah.
has the potential to do work. The
Yes.
potential to do work, PE, potential energy of the spring to do work
Yes.
is
Yes.
1/2. Uh-oh, 1/2 KS. What happened? Who's hacking my system? 1/2 K. And we will learn about this. This is actually the next half. This is actually chapter 14 stuff, by the way. It's the next half of chapter 14. 1/2. Uh-oh. Hold on. 1/2 K delta S squared.
Okay.
I gotta be nice to it. But now, okay, sorry. Okay, that's actually the potential energy, and we could derive that. But here's the difference. We're there. It's a state. That's the amount of potential energy it has at that point.
Mhm.
But here's what's happening here. What is the end? What is the work needed to move the spring from its original undeformed or some certain state, one, to another state? I did work along the path, right? I'm
Mhm.
tracking how I everywhere from 1 to state 2. I did work to stretch it.
Yes.
But here is saying I am here, I have the potential to do work, and this is a measure. So here's the thing, and it's called in your you'll learn about conservation of energy.
Of course.
Conservation of energy is in math they call that it's path independent. Where if you look at conservation of energy, you only care about the endpoints. You don't care about what's happening along the path. You care about what's the energy here, what's the energy here. Remember those in physics where you did, oh, what's the potential energy here and the kinetic energy here? It's kind of balanced. Who cares about what's happening in between? In math, that's called a line integral. The line integral, the sum of the total energy has to be conserved, conservation of energy. But essentially what you says is that you don't care about the path. You
The
just
only
care about
reason why
where
I'm
it's at.
laughing, Dr. Navarro, the only reason why I was laughing is because it is the same exact thing in chemistry. It's the same exact thing in biology. It's the
Yeah.
same exact thing in all the other sciences. That's the only reason why I was laughing. Please do
Yeah.
not take offense in any
I
way
didn't
whatsoever.
even notice that you laughed, but I appreciate laughter because it lets me know that you're awake. But look,
Why would I not be awake around you? What's wrong with you?
I think we need a break. But no, but check this out, right? So now these are very fundamental questions that you should have gotten from physics, but it's reinforced and presented differently, right? But my point is this: that remember when we check the particle here, here's when we go into the energy methods later on, that I care about what's happening here. I care about what's happening here. That's called conservation of energy. Well, then I know I took work to get it to here. So the stuff that we're doing here is we're adding up that it's path dependent because friction could act along the path, right? That's what it was. It's non-conservative forces. But we'll go into it. I don't want to jump too much again. Okay. But here's the point. All right. But Sean, if you still don't get it, when we get to the energy methods, I'll make sure I'll reinforce it. Okay. So this is the energy of to move to displace the spring from 1 to 2 along the path. Different from what is the potential energy of the spring? Meaning I stretch it to here. What's the energy stored in there? The potential to do work, right? But now check this out. What are we going to do to the spring? What are we going to do to the spring? We're going to attach a particle because our analysis is the particle, right? Relative to what's happening to the particle, the net sum of the forces to the particle. So let me ask you this. We got the energy of the string, but what is it doing relative to the particle? Okay, so what I'm going to do is this is neutral, all right? And so now what I'm going to do is I'm going to get my spring and cause the particle to move to the right. So my particle moved to the right, okay? So that means the displacement, if you want to think about your delta S, is to the right. Your displacement to the right. But then what is the force of the spring onto the particle?
To the left.
It's to the left, because doesn't the spring want to oppose its motion?
Yeah.
So right away, that should tell you that, hey, look, that's called negative work. So when you have a spring attached to a particle, the spring is always going to do negative work. And that's this formula here. We got the same formula from the top of just the spring itself. But the question is, what is happening to the particle? It's doing, all you got to do is attach a little negative. And let me show you why it's going to be negative, right? When I pulled it to the right, it's negative, right? Because the force is opposing. This is the force of the spring. So now what happens if I have it the other way? What if the particle moves, let's say I move it to the left from the neutral. What if I squished it, right? This
Positive
is neutral
work.
here. No, it's actually negative work. Let me show you why. The displacement of the spring was to the left, your delta S, correct?
Yeah.
But what happens if you compress a spring?
It
Doesn't the spring doesn't want to push back?
yes.
Yeah. So guess what? The force is now opposite of the direction in which you move. So whether this is the particle's perspective. If I stretch the particle, doesn't the spring want to pull it back? If I
Mhm.
compress the particle toward the spring is going to push back
Mhm.
on the particle. So regardless, the work due to a spring, this is your take-home message. The work of a spring onto the particle is always negative, depending on where it's at state 2 and state 1, with respect to the undeformed length. Okay, we'll go into those details in a bit. Questions? So we got gravity. If I introduce gravity, we know the work of gravity. If I go against gravity, it's negative work. If I go with gravity, it's positive work. When I introduce a spring, no matter how I go, I'm doing negative work.
That's in the formula, right?
Yes. So I did the derivation where it's positive, but that's just only looking at it the perspective of the spring. Doing work to stretch the spring, press the spring. Because if I pull the force of the spring outward, the spring is stretching outward. But if I compress the spring is also moving, right? Because my force is compressing, the spring compresses in that direction. But now what I'm doing is relative to the particle. And Newton's third law says equal and opposite, right? So it's always going to oppose the motion. So just let that marinate, but that's your formula. The one boxed in red. That's the one that you actually use relative to the particle.
Can you explain why it's always negative again, please?
Yeah. So you remember how we talked about, here's the math fancy formula. 1 to 2. Okay. 1 to 2, F dotted with dr. Okay. So then if you look at F dotted with, let's say F dotted with R, right?
Sorry.
Zoom tight. Well, F dotted with R is just F cosine theta times R. And so if, let's say, like, right. So let's say the neutral, nothing's happening to the spring. There's the ball connected to the spring, right? So now what I'm going to do is I ended up pulling on the ball to move it to the right. So that means my displacement is to the right. Do you agree?
Yeah.
Okay. Now, but what does the ball feel? What force is acting on the ball? Or the particle? Doesn't the spring want to go back to its neutral?
Yeah.
Yeah. So if you pull against the spring, then the force of the spring is to the left. And so if it's to the left and your displacement is to the right, the vectors Fs and delta S are like this. The angle is what? 180. So if you plug it into here, 180, you're going to get a negative work. But what I want you, that's the math way of thinking about it. But what I want you to think about is, look, if I'm moving in this direction and my force is the other direction, that's negative, right? You're doing work against you. Friction is negative because you go in one direction, friction opposes you. Make sense? That's how you want to think about it, whether it's gravity or whether it's a spring. Now, what if I go the other way? What if I now move my particle to the left? If you compress a spring, doesn't the force of the particle, doesn't it feel like the spring force is pushing back, right? So in this case, you moved to the left, what the force opposes. So again, the work is negative. Cool. That's why in the formula, we just put a minus in front of the whole energy because it's opposite of the spring.
So like, so it doesn't matter the direction as long as it's opposite. It's gonna be negative. Opposite
Well, it
the-
depends. You have to look at how you're moving
yeah,
and how the force acting.
yeah,
And
yeah.
from that, determine whether it's positive or negative work. For
Yeah.
example, so let's go back to a very simple example. Okay, let's say you're pushing a force 10 pounds, and then you have friction action acting down here, friction. Okay, so if the box is there, and if the box is there, and then the box moves, the box ends up moving to the right, meaning it's actually now over here, state 2. Here's 1, state 2. It moved, it displaced this way, delta S, right? And let's keep the same forces acting on there at all times. Force of friction, force, friction. Okay, so because this is a simplified version, right? Because the box moved to the right, look at this 10 pounds. Is that positive work or negative work?
That's
Positive.
Positive, because the force went along the direction. Now, what about friction? Is that positive work or negative work?
Negative.
Right, because the box still moved to the right, yet the force is opposing motion. That's why it's negative. But it's a reaction. So you could still move to the right. You're not going to move as fast, right? Because you have to look at the net sum of the forces. Cool?
Yeah, yeah, got it.
Awesome. Let me see. Yeah, there's the formula for energy. You have to look at all the energies. I think it's best if I did use T. It's best that if I again do the problems and kind of work through them. How are we doing with time? I know we started later. How are you guys feeling right now?
Good.
Okay, so I'll try to see if I can end by. I'll try to do one problem as quick as I can. I know we started a little bit later, but I want to maximize as much as I can. The units, force times distance is Newton meters. That's going to be a joule. Force times distance is the energy of joules, because energy is going to be in those units. And we'll look at that. But I think what I want to get to, yeah, here we go. Here's the friction one, right? When it comes to friction, when things are moving, we'll look at again an example. Force of friction is it's going to be kinetic friction. It's not going to be static friction, because if it's static, it's not moving. We don't care about it, right? It's dynamic. This causes dynamics, it's motion. So what we're going to do is when you look at the force of friction, kinetic, it's mu k times the normal force. It's equal to mu k, k being the kinetic friction. Kinetic friction coefficient, kinetic, and that's given. Coefficient. Okay, coefficient. Okay, so what's going to happen in order for us to solve these problems? Okay, and I want to just focus on the picture before we do the math. But this is how you kind of strategize. Let's say, okay, let's say that this box was already moving. This is state 1, and then this is state 2. Okay, let's say that this box was already moving with some V1. That right away should tell you, hey, look, it has initial energy, kinetic energy. We'll go back to the main formula we derived at the beginning. But I want you to think about this to see what's happening. Then what's happening on this box? Maybe there's a force caused it to move to the right, right? To move to the right, to go, and it displaced S amount. But what you need to understand is you need to look at the sum of the forces, meaning we go back to our free body diagram. If you do the free body diagram, you're going to have the force moving it to the right. We're going to introduce friction acting on the bottom, opposing its motion. You get your normal force and your weight force. But here's the take-home message. I could go into the wording, reading, and all that, but no. Look, it's important that you realize that how does the box move? To the right. So then only the forces that are along the same direction or even opposite direction can do work. So these here, these are your normal forces which do not do work to move it along the path. So you ignore these in that energy of the work from 1 to 2. You ignore those. And so which ones do you keep? You keep the P force and you keep the friction force. And then how long do they act for? Well, you displaced it S amount, so you have to multiply by that S amount, okay? So if you look at the formula, remember how when you look at the kinetic energy, I'm going to generalize it. You have the kinetic energy 1, right? Plus, see all this term here? See how you have your force, your P force, and then you have your friction force here? Let me highlight it. What you're doing is you're multiplying by how much you displaced it, work times distance along the path. So you're multiplying both by S. But notice that friction is what? Friction is positive. So, but what are these two terms here added? This term is the work to get it from 1 to 2. And if you look at that formula, it's equal to the sum of the forces tangential ds integrate from 1 to 2. That's what this whole thing is, adding up all the forces, either aiding in the motion or opposing the motion. And then what is it equal to? It's equal to the kinetic energy at state 2, because most likely if you push it, it's going to go faster. Okay. So it, again, for these types of problems, what's important is the free body diagram and the general formula that we derived. Any questions on that? I think we will try to do a problem like that that's kind of targets this. Good. Okay. All right. So let's do an example to kind of see how this is going to work. Okay. So and we'll probably see how much we can get to this. Okay. So here's how we're doing this. All right. So now let's look at our box. We have a box here. Okay. And on this box, it's being supported, right? There's a spring kind of connected to it, and then it's being pulled with a force. Okay. And what's going to happen is here, you measure how much it displaces with this S, displacement, the variable. Okay. So here's the, and not only that, but look, the box is already moving with some speed. Okay. So here's what's happening. Do you guys agree that eventually, if this box keeps going down, do you think the box is going to speed up, or what's going to happen to the box if I pull on it?
Slow down.
It's going to slow down, and eventually, it's going to do what?
Go back.
Go. It's going to stop, and then it's going to go back, right? And then, if anything,
Yeah.
it's going to be like this, a dynamic problem, right, where it's kind of like a vibration, assuming no losses, right? So, but here's what the question is asking, right? So we see that the box is moving at a certain velocity initially, state 1. What you see is that initially at s equals 0.6, when s is 0.6, when this length here is equal to 0.6, what does it tell you? That the spring is neither stretched nor compressed, meaning there's no force acting. That's like the undeformed or the equilibrium point. Okay. So what else do you know? That's gonna be very key. What else do you know? That the block has a mass of 10 kilograms, and then it's subject to a force of 100 newtons and has a speed at going down at that instant of 5 meters per second. Another important point is that, hey, it's a smooth plane. What does that mean? That can make our lives a little bit easier. We're going to ignore friction. Okay. So here's what the question is asking. What is the distance s that the box will go down the plane until it stops? What we should trigger you is that the velocity at state 2 is equal to what in the final state?
0.
Yeah, 0 meters per second. Cool. So that means the final kinetic energy should be 0. And so how long did it take for the for the box to travel, the distance traveled is what we need to find. Okay. So the way we're going to use this is our tool of the work energy. Okay, and I'm going to show you how to actually the formula and how to actually draw your diagrams. You're going to get a diagram for this. So recall that, and we'll go back to that. So what you want to think about is let's see if I can remember the kinetic energy for state one, or I think the book uses T. Again, I'm sorry to try to be consistent. I'll use U just because the book has been using U. The kinetic energy for state one, and then you need the energy to go from 1 to state 2. What is this one? This is the energy of the force along the path, right? Is equal to the kinetic energy for state 2. Okay, that's like how I generally have these terms, the notation. So what is kinetic energy state 1? Kinetic energy state 1 is 1/2 the mass of the object times the velocity of the object at squared at state 1. Right? And then what is kinetic energy of state 2? It's 1/2 the same mass, the velocity squared at state 2. Right? That's what we have here. And then in here, U from 1 to 2 is what you need to do is add up, integrate, sum up all the forces that are tangential that are along the path. Right? That's the work to get it from state 1 to state 2. Force times distance. Are we clear here so far? That's the definition of what I derived from before. So what I like to do is be consistent. Pay attention to this this plus minus the plus and then the equals, because what I'm going to do is have a diagram. So see this box here, and it's very similar to remember when we did a FBD KD diagram, the free body diagram, kinetic diagram. I'm going to have a diagram for each one, so it's easy to kind of visualize. So here is the box, right? I'm going to borrow this box here, and then I'm going to have a diagram for the left side. What is the left side measuring? I'm going to have one here. Paste. Copy. Yes. Then I'm going to have one for this one. Oh no. I'm going to have one for this one. I'm going to have one for this one, and then have one for the right side. Okay, and let me kind of show you what I'm talking about here. You guys see what I'm trying to do here? Right, follow the equations, right? So let me first figure out, okay, what was the initial energy of the box when it first started out? Or what was the initial speed?
5 meters per second.
Right, so that's when it started out, right? So what's going to happen is that this is going to have this box has a speed of 5 meters per second. So I like to put my velocity profile here. V is equal to 5 meters per second, right? Initial kinetic energy. And then what is the velocity in the second state? So I guess I can call this V1, right? If you want to call it V1. What is the velocity in the second state? The final state.
0.
0. So if this is 0, what essentially in the math up here, it's going to be 0. And then in the math up here, you can just plug in the mass and plug in the velocity and you're done. Does that make sense? Right? So, but then what is this one here? What diagram is this one? This diagram should be informed by the
step in between.
Yeah, the forces along the path. Right? It's looking at the sum of the forces tangent along the path and how much you displace along the path. Okay? So then you get this information by looking at the FBD. So
So
let me
wouldn't that
focus on
be
the
an
box.
arrow 180 degrees from V2 and V1?
No, so you want to think about this diagram. This one in particular has something different. Okay. So
Sorry.
so sure, no problem. So let's kind of imagine here that let's see, the box. Let me see how I can draw this. Let's say the box is down here. Let's say the box ends up down here. Okay. The box is down there, and it most likely, right? When we said that the box here at 0.6, let's see, 0.6. Yeah, when it was here, we can say that that's like the state one, right? S1. And then eventually for state two, the box went down to state two, right? So that means when it displaced some delta S, which is S2 minus S1. Okay, but it stopped initially, some S amount. So here's how in the diagram for that one, we need to look at the forces acting on the box. Okay, so what do we know about the forces acting on the box? What do you have on this one here?
100 newtons.
Huh?
100 newtons.
Yeah, so we still have the force being applied to the right, 100 newtons. Okay, what else do we have?
Well, change of S or the angle? Change of S, right?
Just look at the forces on the box.
The
State
velocity,
two. Huh?
velocity is 0, right?
Yeah, but think of only look at the free body diagram. Think about the free body diagram.
Gravity.
So we have weight going straight down.
Normal force,
Normal.
Let's see. Yeah, you have a normal force,
friction.
and then you have a normal force,
Oh no,
and then what else? And no friction, because otherwise, if there was friction, I would have a friction like this. Where's the friction?
The spring force pulling it back.
Oh, so now I'm going to ignore friction, and so then I'm going to have a force of the spring. Clear so far? Okay. All right. So what I need to do, this is I'm going to copy this. All right. This here is not the free body diagram. It's the sum of the forces along the path diagram, right? But it's informed based off of what? The free body diagram, if that makes sense. So let me move this a little bit to the left here, and I'm going to copy it here. So if I look at the, right, this is how much work it takes. This is force is not work, right? You need to multiply by how much you displaced. Does that make sense? So how much did you displace?
Change of S.
Yeah, do you guys see that? So change of S is like how much we displaced from state one to state two to move it, which is this one here. And let me make sure I have the correct notation. Give me 1 second here. I'll pause here in case you have any questions. Does that make sense? Like state one initially, right? Initially was here, right? Initially it was there, and now it's at state two. And so I moved it from state one to state two. So the difference between that state one and state two is delta S. Okay. So state one, delta S is state 1 minus state 2. Can put this on the side right here. Okay, so what does this term, fancy little calculus term, mean? That you have to sum up all the forces that are tangents, right? Meaning every force acts over delta S. We don't know what delta S is because that's what the whole goal is to find out what it is. Oops, it's S2 minus S1. Okay. So what we need to do is solve for that change in displacement or the final length it went down to. So every single force you see here, here's the new stuff, right? What we need to do is integrate the force of that one along the S. Integrate the force of this one. I'm going to leave it as let me see. I'll leave it as 100. Integrate the force of this one from 1 to 2 of 100 ds, and then do it for all of them. Integrate the force
But
of
didn't we
n.
say they like the forces that are perpendicular? We just don't count.
Excellent. That is correct. Because if you look at this force here, it is not along the path, right? So this becomes 0. We ignore it. Okay. But remember, doesn't gravity help you? Meaning if I look at this axis here, let me go down. Like this is the path axis, right? I don't like to go back to the X, Y. I'm just going along the path. Whatever axis this is the S axis, right? S axis. So it's going along that incline. Look at the weight vector. The weight vector has 2 components, right? The weight vector has this component, weight normal, and then it has, I'll draw a different color. I want to distinguish between them. The weight is technically going down, but the weight vector actually has a normal component and a tangent component along the path. Do you guys agree? And this angle inside is going to be, you guys look at the geometry, 30 degrees. And it should make sense, right? Because let's say I take off the spring, right? You think the block is going to come down the ramp due to gravity. Forget the forces and all that, just gravity. Will the block slide down?
Yes.
Yeah.
And the reason why is because there's a component of the weight gravity helping you go down, which is the weight tangential. Okay. So when you do the integral, see this normal force? That one doesn't do any work. However, this one does work. Does that make sense? What is, right? If the forces are constant, what if the forces are, let's take, for example, let's just focus on the forces, okay? Let's just focus work to forces. So that's kind of like the diagram. You pretty much integrate, right? I'm following the model, force times ds, force is tangent. You integrate. Well, essentially, I mean, you don't really have to do calculus because the force is already constant. It's already along the path. So work due to forces. Moving it from 1 to 2, right? So the general formula is this: 1 to 2, summation of forces P ds. So let's look at the summation of forces, but let's just kind of break it down. Let's look at the work due to the applied force. What is the work due to that one? Force times distance. What's the force? If you look at the math, it's like this: 100 ds, right? But we said that, I mean, I already know it's going to displace delta S, right? And the force is already, and I'm talking about this one. Let me see if I can highlight it. See that one? It's kind of pushing it down the ramp. So I can just simply say, if I integrate it, it's just going to be 100 times delta S, force times distance, because the 100 newtons is already along the path. And it's positive work because they're both going in the same direction. Does that make sense? Where again, what is delta S? Delta S is the displacement along the path. And this force 100 is along the path already. Does that make sense? So that work due to that force is done right here. 100 times delta S. So what are the other vectors here? Don't we have the weight component? Weight work. But the one that we care about is the weight that is what? Along the path. So if you look at the weight, you care about only the one tangent or along the path. That's WT. But how do we get that? If you know the angle of 30 degrees, and the way you get 30 degrees is, you see the incline is 30. And so if you go like this, and you start to, if you move this 30 degrees here, right, to the vertical, the normal, the ramp gets squished down, then this moves 30 degrees here. Okay, so that gives you the 30-degree angle for the weight. All right, so because the weight is 30 degrees to the normal, then the weight, you go back here, the weight, you're going to integrate the weight component, right, times ds. I'm ignoring the weight normal, right, because again, it's normal to the path. It's not going to do any work. So if you integrate it, well, what is WT? WT is W sine 30 degrees. And it's constant. It's always going to have a sine component because the ramp is the same angle. And then you integrate 1 to 2 of ds, which essentially is W sine 30 delta S, where again, delta S is S2 minus S1. What is the weight? G, let me go back up. What is the mass? 10 kilograms. Okay, so it's 10 kilograms times 9.81. So let me ask you this: is the weight being done? And I'm not gonna finish it, I'm getting there, but probably go for 3 more minutes. Is the weight tangent pushing the block down the ramp? Is that positive work or negative work due to gravity?
Positive work, right? Because it's pushing it downwards.
Yes. So the weight gravity is pushing it down.
How?
Okay. Because there's a component. If you put a, or here, let me give you this example. There's ice on the roof. Okay. There's a brick on the roof. What's going to happen to the brick?
It will
On
slide
ice.
down.
That's your how.
What? Repeat, please.
It's gonna
slide
slide
down?
down. Why?
Uh-huh. Yes.
Why does it slide down?
Because there's gravity.
There you go. Because of the effect of gravity.
Yeah.
That's why. Oh, here, let me break it down. If you look at the free body diagram, you're gonna get the block has a normal force
Normal. Yeah.
and then
Then
has
weight.
a weight force.
Yeah.
But let me break it down. The weight force itself has a component normal to the roof.
And tangential, correct, which is parallel to the roof.
Mm-hmm. So it has a component. God, let me see. Okay, it has a
Gee.
component normal weight
Uh-huh.
normal, and it has a component weight tangent to the roof. So
Which is parallel. Yeah.
yeah, so this one they're balanced out. It's called static
Yeah.
equilibrium. But
Yes.
nothing, at least in this example, this brick example, nothing is balancing out the weight tangential. And because nothing is balancing out, that's why this brick is going to fall down the ramp.
But what if we have make it into a rough roof? We have
Then
like
you have friction, and
yes.
it's going to oppose its motion. Friction does
Yes.
negative work, but it could still fall down because friction is less if the friction is high enough, that's called static friction.
Correct.
But if you overcome that static friction, then you have a net force opposing, actually going down the ramp. But the net is still less than as if you have ice, right?
Yeah.
Okay.
Unless
So,
you want to destroy your roof, that's why you put friction there.
right. Is this clear, everyone? Sort of.
But if it goes there,
Right.
no, that would make it negative.
Mhm.
So negative
Oh no,
tangent.
this if it goes down, this is positive work
Okay.
because the weight vector is pointing along the same direction as the box or the box or the brick moves.
Okay.
Okay, so now I don't know if you guys caught it from before. The actual formula was y delta weight times delta y, right? What I did here is I purposely broke down the weight vector. I don't know if you guys remember when in the lecture I said, let's leave the weight alone, right?
Mhm.
Because we're so used to leaving the weight by itself, it's always acting down. So I'm going to show you that version and I'll stop. Okay. So what I did is I projected the weight onto the direction. I projected the weight onto the direction of path of motion. Dot product, you can cast shadows onto each other. It doesn't matter. Right. So I'm going to show it to you that way. So here's what I just said. The box, I'm going to use this brick example here. Okay, so for example, this brick, if this brick moves delta S, right, from here to here, from here to here, delta S. Okay, the weight component, if this, do we agree that if this is theta, right? Let's see if I can draw it. I'm gonna draw the. Let me see. I'll draw the box by itself. Or the brick, or whatever's on the roof. So the weight was down, right?
Mhm.
And then here's your weight in normal, and then here's your angle theta,
Weight tangential.
and then weight tangential is this component, right?
Yeah.
Weight tangential. Okay. So essentially, what I'm trying to prove to you is weight dot the dot product. So can we agree that if the box was here, now it is here, right? It displaced some
Delta S.
delta S from state 1 to state 2 along
Correct.
the roof. Okay.
Yeah.
So then what is that work? Well, I looked at the force along the path. What's the path distance? Delta S.
Delta
What is the
S.
weight along, what is the force along the path? WT. And so according to, if I know the weight W, how do I get the work done from 1 to 2? It's WT, which is W sine of theta, delta S.
Uh-huh.
Sound good, everyone?
Yeah.
So now I want you guys to think about it this way, this perspective. And by the way, this angle to the horizontal was theta, right? The roof angle. So
Yeah.
here's the other way of doing it. So this tests whether you're very comfortable with dot product, right?
Oof.
Now I want you guys to think about it this way. That I want to leave my weight alone. Because if you look at the slide, the weight is chilling, it's by itself, it's just W. But
Mhm.
we know that gravity only, right? So the idea here is this, that the vectors have to be along the same direction. Okay.
Yes.
So if you look at delta S, right? Delta S is like your displacement vector along the path. So, but delta S goes along, this is your delta S here. This is your, let me draw your delta S displacement on the side. So you see how this distance from here to here is delta S. So let me draw delta S. Okay. And the angle to the horizontal, the roof angle, which is given in the problem
30
is
degrees.
theta, right? And
Yeah.
it's 30 degrees. So, but here, I'm going to keep it general. But my weight only acts in the vertical, right? So why don't I find the distance that is along the weight direction? And so now I want to leave weight by itself, and I'm going to modify delta S. So the distance along the weight
Sine
direction is
theta.
that distance. Do you guys agree?
Yeah.
Right? So that distance is delta S sine theta, which is why the book calls it delta Y, because this distance is along the Y direction. So if you look at it, how much work did the box do? Well, all you got to do is find your delta Y distance. And so how did it do work? It was work force times the distance, right? The force, I left it alone and I only got the distance along the direction of the weight. It's a different perspective, right? Because gravity only acts to the Y if you think about it. And so if I do this, it's W times what? W times,
Delta sine theta.
yeah, I should do sine theta
Delta S sine theta.
times delta S. But, I'm going to do a little bit of fancy math here. Well, let me see, W delta S sine theta, right? Just
Yeah.
manipulate it. I'm going to get the same answer regardless. But what I like to do is think about it, keep reinforcing at the beginning as simply as I can. If the force is going in the direction, you got to make sure the displacement is going in that direction. That's how I like to think about it. But if the weight is this direction, we'll find the distance along that direction. Okay, so I'll stop there and let it marinate, and we'll finish up this problem last time. But I want you guys to kind of jump ahead and start doing do the reading for this, and then do some example problems. But we're pretty much getting there. That's probably the tricky part to this. Any questions as to what we're doing
No.
so far? We've got 2 down. We just need 2 more, and then we'll just put it all together. Okay. Unless you guys have any other questions, please let me know. Have a good rest of your weekend. Be on the lookout for those quizzes, and stay safe.
Professor,
Yeah, Daisy.
can you move it a little bit more to where it was?
Yeah.
Okay, thank you.
All right. Good seeing everyone. Take care and be safe. Any other questions?
Thank you, Professor. Have a good
Mike.
weekend.
You too.
Thank you.
All right. Adios. Oh no, Daisy, were you copying it, huh? Here.
It's okay. I finished.
Okay.
No, I need it. Okay, there.
Oh.
Thank you.
I'll leave it there.
All right. Thank you so much.
No problem.
Professor, can you upload this week's lecture videos?
For which one?
I think it was
Static?
Tuesday and today's.
Oh, I didn't do. Okay, I know I didn't. Just before I upload it, I think strengths in my statics is getting all 11. See, I'll do that right now.
Okay.
Thank you.
Okay.
Today's it's gonna take a little bit of time for it to process. It always does it at the end of at night. So it just takes a while. I'll stop the recording now actually, so I can start doing it.